Welcome back to Sujit Patil Tech, your premier source for engineering and technology insights. In our Gear Metrology Series, we've covered essential topics on all types of gears. If you missed any parts, catch up on my YouTube channel, Sujit Patil Tech. Today, we will continue with Gear Terminology Part 2. If you haven't watched Gear Terminology Part 1 yet, please do so on my YouTube channel before watching Part 2. So let's get started. 12 diameter pitch (dp). An imperial unit for gear tooth density. Diametral pitch (dp) is a unit of measurement specific to imperial gear systems, those using inches as the base unit. It offers an alternative way to describe the size and tooth count of a gear compared to circular pitch. Understanding diametral pitch. Definition: diametral pitch is the number of teeth per inch (TPI) on a gear's pitch circle. In simpler terms, it represents how many gear teeth are crammed into every inch of the pitch circle diameter (PCD). Relationship to circular pitch. Diametral pitch and circular pitch are inversely proportional. A larger diametral pitch, more teeth per inch, translates to a smaller circular pitch, less space between teeth. The following formula relates them: dp is equal to 1 circular pitch. Applications. Diametral pitch is primarily used in the United States and some other countries that follow the imperial system for gear design. Benefits. Diametral pitch can be a convenient way to estimate the size and tooth count of a gear, especially for those familiar with imperial units. 13. Module M. The metric gear's universal tooth sizing unit. The module M is the hero of metric gear systems, playing a similar role to diametral pitch (dp) in imperial systems. It's a fundamental unit that defines the size and tooth count of a gear based on the pitch circle diameter (PCD). Understanding the module. Definition: the module is a unit of measurement specifically used in metric gear systems, those using millimeters as the base unit. It represents the ratio between the pitch circle diameter (PCD) in millimeters and the number of teeth (Z) on the gear. The formula is M is equal to PCD mm Z. Simplicity. The direct relationship between module, PCD, and number of teeth allows for easy calculation and gear selection. Standardization. Gears with the same pressure angle and module value are generally interchangeable, promoting ease of use and maintenance. Scalability. The module allows for scaling gear sizes proportionally while maintaining proper tooth proportions. 14. Clearance. The vital space between meshing gears. In the world of gears, clearance isn't about making room for extra belongings. It's the crucial space between the teeth of mating gears that ensures smooth operation and prevents binding or damage. It's essentially the gap that prevents the teeth from grinding against each other. Understanding clearance. Definition: clearance refers to the minimum amount of space between the tops of a gear's teeth, addendum, and the bottom of the mating gear's teeth, dedendum, at the point of meshing. Smooth operation. Clearance allows for smooth engagement and disengagement of teeth during meshing, minimizing friction and noise. Gear life. Adequate clearance prevents excessive wear and tear on the teeth, extending the lifespan of the gears. Thermal expansion. Gears can expand slightly due to heat during operation. Clearance accommodates this potential expansion, preventing binding. Factors affecting clearance. The amount of clearance can be influenced by several factors. 15. Total depth, H. The gear tooth's full reach. In the realm of gears, total depth, also known as hole depth, signifies the complete height of a gear tooth. It's a crucial dimension that defines the overall size and engagement characteristics of the tooth. In simpler terms, imagine the total depth as the entire length of a tooth profile from its peak, tip, down to its base, root. Understanding total depth. Definition: total depth, H, represents the distance between the top of a gear tooth, addendum, and the bottom of the tooth space, dedendum, measured radially from the pitch circle. Meshing and strength, the total depth, along with the pressure angle, determines the depth of engagement between mating gear teeth. A larger total depth can provide stronger teeth but may also lead to deeper tooth interference during meshing. Relationship to other parameters. The total depth is directly related to the addendum H_A and dedendum H_F of a gear tooth. The following formula expresses this relationship. Total depth, H, is equal to addendum H_A plus dedendum H_F. 16. Working depth, H_E. The engagement sweet spot between meshing gears. Working depth, a crucial concept in gear design, defines the depth of engagement between two mating gear teeth. It's the sweet spot that ensures smooth operation and efficient power transmission. Understanding working depth. Definition: working depth, H_E, represents the distance between the top of a tooth on one gear, addendum, and the top of a mating tooth's space, dedendum, at the point of meshing. Smooth meshing. A proper working depth ensures smooth engagement and disengagement of teeth during meshing, minimizing friction and noise. Strength and efficiency. Sufficient working depth allows for strong tooth interaction, transmitting power efficiently. However, excessive working depth can lead to deeper tooth interference, causing binding and increased wear. Relationship to other parameters. The following formula expresses this relationship. Working depth, H_E, is equal to addendum H_A of gear 1 plus dedendum H_F of gear 2. 17. Tooth thickness. The gear's grasping power. In the world of gears, tooth thickness isn't about a gear's waistline. It refers to the width of a gear tooth at a specific reference point, which plays a crucial role in meshing strength and overall gear performance. Understanding tooth thickness. Transverse tooth thickness. This refers to the arc length of the reference circle between the two sides of a tooth profile. Imagine looking at the end face of a gear and measuring the distance along the pitch circle between the two flanks of a tooth. Normal tooth thickness. This signifies the shortest distance between the two sides of a tooth trace measured perpendicular to the reference circle. It's essentially the width of the tooth at a specific point, like its base or tip. Strength and power transmission. Thicker teeth can handle higher loads and transmit more power. Clearance and meshing. Tooth thickness needs to be balanced with proper clearance between mating gears. Gears with very thick teeth might require larger clearances to avoid binding. 18. Tooth space, T. The room between gear teeth. In the intricate world of gears, tooth space isn't about a gear's personal distance. It refers to the gap between two adjacent teeth, a crucial element for proper meshing and gear function. Understanding tooth space. Definition: tooth space, also known as tooth gap or intertooth space, signifies the distance between corresponding flanks of two adjacent teeth on a gear. Meshing and clearance. Adequate tooth space allows for smooth engagement and disengagement of teeth during meshing. It provides the necessary clearance to prevent the teeth from grinding against each other, minimizing friction and wear. Strength considerations. While thicker teeth can offer more strength, they also require larger tooth spaces to maintain proper clearance. The tooth space is directly related to the tooth thickness and the circular pitch (CP) of the gear. The following formula expresses this relationship, where T represents tooth space, T is equal to CP, tooth thickness. 19. The face of the tooth. The functional surface of gear engagement. In the realm of gears, the face of the tooth isn't a gear's expression. It refers to the functional surface of a gear tooth that makes direct contact with the teeth of the mating gear during meshing. Understanding the face of the tooth is essential for appreciating gear function and design. Understanding the face of the tooth. Definition. The face of the tooth is the entire functional profile of a gear tooth, encompassing both the involute flank surface and the top, tip, of the tooth. Meshing efficiency. The involute profile of the face allows for smooth engagement and disengagement of teeth, minimizing friction and noise. Power transmission. The face of the tooth transmits power between the gears as they mesh. The strength and design of the face are crucial for efficient power transfer. Contact and wear. The face of the tooth is the primary area that experiences wear and tear during operation. Proper lubrication and material selection are essential for minimizing wear and maintaining smooth meshing. 20. The flank of the tooth. The sloped partner in gear meshing. Within the intricate world of gears, the flank of the tooth isn't a weakness or a surprise attack. It's the sloped surface of a gear tooth that plays a critical role in meshing and power transmission. Understanding the flank is essential for appreciating gear function and design. Understanding the flank of the tooth. Definition. The flank of the tooth refers to the two inclined surfaces on either side of a gear tooth. These sloped surfaces are not flat but rather follow a specific involute curve profile. The importance of the involute curve. Most modern gears utilize involute curves for their tooth flanks. Smooth meshing. The involute curve ensures smooth engagement and disengagement of teeth during meshing, regardless of slight variations in center distance between the gears. This characteristic prevents jerky movements and reduces noise. Constant velocity ratio. Gears with involute flanks maintain a constant velocity ratio throughout their mesh cycle, which translates to smooth and efficient power transmission. The two flanks. A gear tooth has two flanks. Driving flank. This is the flank on the leading edge of a tooth during meshing. It pushes the tooth on the mating gear, transmitting power in the intended direction. Driven flank. This is the flank on the trailing edge of a tooth during meshing. It experiences a pushing force from the mating gear's driving flank. Impact on gear design. The design of the tooth flank profile, including its pressure angle and curvature, significantly affects gear performance. Strength and wear. The flank profile needs to be robust enough to handle loads and minimize wear during operation. Interchangeability. Gears with standardized pressure angles and flank profiles can be easily interchanged without compromising meshing characteristics. 21. Top land. The gear tooth's protective cap. In the world of gears, the top land isn't a prestigious piece of real estate. It's the narrow, flat surface at the very tip of a gear tooth. While it might seem insignificant, the top land plays a crucial role in protecting the gear and ensuring smooth operation. Understanding top land. Definition: the top land is a small, typically flat surface located on the extreme top of a gear tooth profile. It extends outwards from the involute flank of the tooth. Strength and wear protection: the top land reinforces the tip of the tooth, making it less susceptible to chipping or breaking under heavy loads or impacts. It acts as a protective cap, preventing damage to the working area of the tooth profile. Clearance and interference: the top land helps maintain a small amount of clearance between the tips of meshing gears. This additional clearance minimizes the risk of interference between the tips, especially during high-speed operation or under misalignment conditions. 22. Face width B. The gear's breadth of engagement. In the realm of gears, face width isn't about a gear's expressiveness. It refers to the axial width of a gear tooth, signifying the length of the tooth along the axis of rotation. Face width plays a crucial role in gear strength, load capacity, and overall performance. Understanding face width. Definition: face width B represents the distance measured parallel to the gear's axis of rotation between the two opposing faces of a gear tooth. Imagine slicing the gear perpendicular to its axis and looking at the end face. The face width would be the length of a single tooth along that face. Strength and load capacity: a wider face width distributes the load across a larger area, increasing the gear's overall strength and load carrying capacity. Wider faces can handle higher torque and bending forces. Effective face width: in situations where gears have different face widths, the effective face width is the one that matters for strength calculations. It's typically considered to be the width of the narrower gear. 23. Gear tooth profile. The shape that defines gear meshing. In the intricate world of gears, the profile isn't just a fancy biography. It refers to the specific shape of a gear tooth, encompassing all its features from the top land to the root. Understanding the profile is fundamental to appreciating how gears mesh and transmit power efficiently. Understanding gear tooth profile. Definition: the gear tooth profile is the complete two-dimensional shape of a gear tooth, including the top land, face, involute flank, dedendum, including the root, and any chamfers or modifications. It defines the way the tooth interacts with the mating gear during meshing. Meshing efficiency: the profile dictates how smoothly the teeth of two gears engage and disengage during meshing. A well-designed profile minimizes friction and noise, ensuring smooth power transmission. Strength and wear: the profile needs to be robust enough to handle the intended loads without excessive wear. The pressure angle and overall tooth thickness influence the profile's strength characteristics. Common profile types: the most common profile type for modern gears is the involute profile. This unique mathematical curve ensures smooth meshing even with slight variations in center distance between the gears. Design considerations: gear designers carefully consider various factors when defining the tooth profile, including pressure angle: this angle between the pressure line, normal force, and the tangent to the involute curve at the point of contact significantly impacts meshing smoothness, strength, and potential for interference. Addendum and dedendum: these dimensions define the overall height of the tooth and influence the depth of engagement between mating gears. Fillet and chamfer: these are small modifications at the root and tip of the tooth profile to improve strength and manufacturability. 24. Backlash. The play between meshing gears. In the world of gears, backlash isn't a negative reaction. It refers to the amount of permissible play or looseness between the teeth of meshing gears. While minimal, a certain amount of backlash is crucial for smooth operation and longevity of gears. Understanding gear tooth profile. Definition: backlash is the angular or linear movement between two meshing gears when one gear is held stationary and a slight force is applied to rotate the other gear. It represents the amount of space between the tip of a tooth on one gear and the flank of the mating tooth on the other gear. Excessive backlash versus insufficient backlash. Finding the right balance for backlash is crucial. Excessive backlash. Too much backlash can cause noise, vibration, and potential tooth impact during sudden load changes. It can also decrease positional accuracy. Insufficient backlash. Gears with very little or no backlash can bind or seize, leading to increased friction, wear, and potential damage. Factors affecting backlash. Several factors influence the amount of backlash. Manufacturing tolerances. Slight variations in tooth thickness and profile can affect backlash. Center distance. The distance between the gear centers can influence backlash. Gear design. Design choices like tooth thickness and profile curvature can impact backlash. Specifying backlash. Backlash is typically specified as a tolerance range in angular or linear units depending on the application. Gear manufacturers and standards define recommended backlash values for different gear types and sizes. Thanks to watch my video. If you like this information, just like this video, and for such kind of information subscribe my YouTube channel Sujit Patil Tech. In next video we will learn gear terminology in Hindi language. Thank you.